Okay, so today I'm going to talk about section 11.1, the sequences. So this is outline. So I'm going to talk about definition of a sequence, the convergence and divergence of a sequence. Third one, how to check if a sequence converges or diverges. So what is like a sequence? The sequence is a list of numbers written in a definite order. So A1, A2, A3, A4, like AN, and so on. So we have the infinite numbers. This is like infinite numbers. A1 called the first term, A2 second term, AN nth term. This is like a terminology. This is notation. What's the notation of a sequence? So we use this notation. The sequence A1, A2, A3, and so on is also denoted by the set notation of AN. The set notation of AN from n equal to 1 to infinity. This is like a notation. Example. The n over n plus 1 from n equal to 1 to infinity. So what's it like a list of numbers? We can write like this. Here we have, this one is this one is, what's it like A1? Do you know what is A1? Yep, you plug 1 into n. Plug 1 into n, exactly. 1 over 1 plus 1 is the 1 over 2. So A2, similar. You plug 2 into n, 2 over 2 plus 1. So A3 is 3 over 3 plus 1 and keep going. So what's that? So this sequence is the first one, 1 over 2. The second term here, 2/3. The third term is 3 over 4. This is 4 over 5. And keep going. The nth term is n over n plus 1. And keep going. This is exactly the sequence. So like this. Second one. The final formula for the general term an of the sequence. So the first term a1 is 3 over 5, this one. So what's a2 here? The negative 4 over 5. A3, 5 over 125. A4, negative 6 over 625. A5, 7 over 3,125, and so on. So how can you find general term an? So you need to find the sum relations. What is like the relation of this kind of things? So here. This one is the exactly the what's like a relation between this index 1 and 3. What's the relation? What's the relation between index 2 and 4? What's the relation between 3 and 5? What's the relation between 4 and 6? What's the relation between 5 and 7? Do you know? We have some pattern or some relation of index and numerator. Could you find? Oh yeah, this is like n plus 2, you're right. The 3 is exactly 1 plus 2. The 4 is index 2 plus 2. The 5 is index 3 plus 2. The 6 is index 4 plus 2. This is like idea. So we have exactly index plus 2 over the same. This is index plus 2. This is index plus 2. So this is index plus 2. So like this one. This is like exact idea. The next one. What's the relation between index and denominator? The 1, 5, 2, 25, 3, 125, 4, 625, 5, 3,125. What's the relation? So 5 to the power n, you're right. This is exactly 5 to the power index. The 5 to the power index. The 5 to the power index 3. The 5 to the power index 4. The like this. This is like idea. So next one. Was it like the sign? The sign is exactly, this case is first one positive, second one negative, third one positive, fourth one is negative, fifth one is positive. Like a sign changes alternately, right? Positive, negative, positive, negative, positive. This is like exact pattern. How can you denote this pattern? The positive, negative, positive, negative. So do you know how can you write this kind of pattern by using index n? Do you have any idea? So let me see. So from here, we can write the exact an. The an is exactly n plus 2 over 5 to the power n. This is exact the relation. So what's it like alternating things? We have two possibilities. Minus 1 to power n. The minus 1 to power n minus 1. Or this is the same to the minus 1 to power n plus 1. Exactly same. So here, you can plug n equal to 1 into n. So this is minus 1 to 1 is negative 1. You plug 2, the minus 1 squared is 1. Minus 1/3 is 1 to the 3 is exactly minus 1. Minus 1 to power 4 is 1, and keep going. So this case, you plug 1 into n, minus 1 to 1 minus 1 is minus 1 to 0, or minus 1 to 1 plus 1 is minus 1 squared. So exactly 1. The second term, plug 2 into n, minus 1 to 2 minus 1 is minus 1 to 1, minus 1, the 1 minus 1. So what's that? Here, positive 1, negative 1, positive 1, negative 1. Exactly second case. So answer is minus 1 to power n minus 1, or minus 1 to power n plus 1 times n plus 2 over 5 to the power n. This is like a whole idea for this case. Like this. Yep, this is like exact definition of the sequence. So next, convergence and divergence of a limit. Definition: a sequence an has the limit, and you write limit of an as n approaching infinity equal to L. So what does it mean? The an approach L as n approaches infinity. So definition is like this. We can make the terms an as close to L as we like by taking n sufficiently large. This is like exact definition of limit of a sequence. So here, sequence an converges. So what does it mean? Limit of an exists. What does it mean that exists? So limit of an is exactly one finite number. So this an is finite number. A finite number, this meaning. Sequence an diverges if limit an does not exist. Does not exist. This is like idea. So here, this is like a case. This is like n. The A1 is here. This is A2, A3, A4, A5, A6, A7, A8, and so on. So what happens? N is like increasing. What happens? This AN approaches to L. So exactly like this. In this case, sequence AN converges. Like oscillating a little bit, it doesn't matter. This is N is increasing, A1, A2, A3, A4, A5, A6, A7, A8. So what happens? Like oscillating a little bit, but approach to L. So this is same. Limit of AN is L, sequence AN converges. This is like the one idea. That's good. So I want to give the one example here. So sequence 1 over n. Sequence 1 over n. So this is converge or diverge. Converge or diverge. What is the answer? What do you think? Converge or diverge? Diverges. Diverges. So check. Limit n approaches infinity 1 over n. So n is going to infinity. The 1 over infinity is 0. What happened? Limit exists. So answer is like this. Sequence 1 over n converges to 0. This is answer. Is right? This converges. So another example. So what is sequence n? Converge or diverge? Converge or diverge? Sequence n. So what do you think? Converge or diverge? Answer is it's the same. You calculate this one. Limit n approach infinity, the an. The an is just n. What's the limit of n? What's the limit of n? So do you know answer? Yeah, n is approaches infinity. So like this. So what happens? Limit does not exist. Infinity is not finite number like divergent. So like this. This is idea. Does it make sense? So the next one, so we think about how to check if a sequence converges or diverges. Theorem. The limit of f of x equal to L and f of n equal to an. N is an integer. Limit of an is also L. So we have one good example, the previous one here. Do you know this one? No. Sequence n over n plus 1. I want to calculate limit n approaches infinity, n over n plus 1. So do you know answer? What's like limit n over n plus 1 as n approaches infinity? Answer is, this is not improper. Though this is not, what's like improper? Improper is just integral problem. So integral like a to the positive infinity, the f of x dx, that we call improper integral. In this case, we don't call it improper. So do you know this one? We can replace m by x. We can use this kind of like a theorem. You can change it to the like this. Do you remember section 6.8, the L'Hopital rule and relative rate of growth? Do you know that? And this is x, sorry, x. X value approaching infinity, top one is going to infinity, bottom one is infinity. How can you solve? We can use L'Hopital rule or relative rate of growth. I want to use relative rate of growth. You have to ignore constant. It's the same to limit x value approaches infinity, x over x. X is crossed out, just 1. So similar, we can use same idea. So we can regard n as like a function. We have to ignore 1, cross out n, answer is 1. So what's that? Sequence converges to 1. This is idea. Does it make sense? So only like limit problem, only regard n by like x, n by x, and solve by using all kind of limit problems in like chapter 6 and chapter 6. So we can learn a lot of limit problems and the L'Hopital rule and the relative rate of growth. You can use these kind of ideas. So like this, the example. The limit x value approach infinity 1 over x to the r equal to 0 if r is greater than 0. The automatically limit of 1 over n to the power r, n approach infinity is 0 if r is greater than 0. The one example is, we already know this one. Limit x value approaches infinity 1 over x squared. The answer is the 0. We know that. So automatically limit 1 over n squared. Replace x by n. We have same result. Only regard n as x. N as x. We have same result. Like this. So it's good. So this is idea for solving this kind of problem. The limit laws for sequences. We have the limit laws. What are the limit laws? So if sequence AN and sequence BN are convergent sequences, C is a constant. How can you calculate limit of AN plus BN? You can distribute limit, the limit of AN plus the limit of BN. Limit of AN minus BN is the same. The distribute limit of AN minus limit of BN. Limit of C times AN, you can take out C, the C times limit of AN. Limit of C, what's the limit of C? Do you know limit of C? What's that? What's the limit of C? C, 0. So I'm going to give the one example. Limit of 5 and approaches infinity. Like a limit of 5 and approach infinity, the limit of constant is always what? Constant 5. So this is like idea. The limit of C is, yes, C. Limit of an times bn, distribute limit to the first and the second one. The limit of an times the limit of bn. Limit of an over vn similar. The distribute limit to the top and the bottom one if limit of bn is not equal to 0. What's the limit of an to the power p? So we have the like this. P is greater than 0 and an is greater than 0. This is like that makes sense. Because I'm going to give one example. Limit the n approaches infinity. So we have 2 over 1 over n to the power 3. How can you solve? In this case, the limit is going to inside. This is possible. So we have inside one limit. The n approaching infinity. So we have 2 plus 1 over n. It's a whole power 3. So how can you do that? So this is like 1 over n. You can distribute this limit of n here. This 1 over n approach to 0. Exactly only 2. 2 cube is like 8. So we have this answer. This is already true. So like this. So how can you solve this problem? So we have 2 methods possible. The first method is only multiply top and bottom by 1 over n square. The next distribute 1 over n square. So like this, distribute 1 over n square. So like this. So we have 3 minus, is right? 3n squared times 1 over n squared, n squared is crossed out, 3. The minus 4n times 1 over n squared, only 1n crossed out. The negative 4 times 1 over n. The 1 times 1 over n squared is 1 over n squared. Similar. You can distribute 1 over n squared. So we have n squared times 1 over n squared, n squared is crossed out, 1. 2 times 1 over n squared is like this. Next, n is approaching infinity. So what happens? 1 over n is going to 0. 1 over n squared is going to 0. 1 over n squared is going to 0. So answer is 3 over 1. 3 over 1 is 3. This is idea. So like this. Right? So like this. The another method is we can ignore lower terms and cross out n squared. Answer is 3. This is another method for solving this problem. The next one, we think about squeeze theorem. The Bn is between An and Cn, like this. For n is greater than or equal to n0. And limit of An and limit of Cn equal to L. What happens? Middle one. The limit of Bn is also L. So we call squeeze theorem. The next one. This is An is smaller, Cn is greater. The Bn is between A and Cn. So A and Cn approach the same number L. They'll approach the same number L. What happens to Bn? Bn is also approach to L. This is like very clear by using graph. The algebraic method is possible. So we have this inequality. This one. The Bn is between A and Cn. The next, take limit. The take limit, take limit, take limit. So limit of an is the L. The limit of Cn is the L. So we have used this idea. What happens in middle one? The middle one, limit of Bn is between L and L, exactly L. This is whole idea. We have the one theorem. The limit of absolute value of An is 0. Limit of An is also 0. This is like true. So how can you prove? The proof is like this. The An is between minus absolute value of An and the An. Does it make sense? The one example is somewhere here. An equals like a positive number. So what happens? In this case, absolute value of An is also 5. So the An is exactly between the minus absolute value of An, exactly absolute value of An, because An is 5, minus N is like minus 5, absolute value of An is like 5. Yes, the inequality is like true. Yes, same. So An is like a negative number. We have same result. So like this. Only difference is here. Yes, the same. So this statement is always true. So An is between the minus absolute value of An and absolute value of An. The next, take limit to each side. Here, you can take out minus 1. This is same too. Take out negative limit. And approach infinity. Absolute value of An. The limit. And approach infinity, just An. And limit of absolute value of An as n approach infinity. We have this one. We can use this assumption. The limit of absolute value of N is 0. This is going to 0. The right hand side is going to 0. The left hand side is going to 0. Right hand side is going to 0. The middle one is also 0. So we have this conclusion, so like this. So we have one good application. So we think about this one. What is the limit? N approach infinity, negative 1 to power n times 1 over n. What do you think? What is the answer of this question? So what is the answer? The answer is, what is the answer? So what do you think? Was it like a limit of minus 1 to power n times 1 over n? Answer is, do you have any idea? Answer? Okay, the infinity. So here, so we have two methods possible. The next one. The first idea is I can draw the like graph. So what does it mean? The minus 1 to power n to the 1 over n. So I can draw the right some the all terms of a sequence. N equals 1. N equals 1. The first term is exactly minus 1. What's the second term? Plug 2 into n. Minus 1 squared times 1 over 2 is 1 over 2. The third term is negative 1/3. The first term is 1 over 4, and so on. You can sketch the graph, what happens. So graph is like this. Here. This is like n. The first term is minus 1. This is the first term. The second term 2, we have positive 1/2. The third one is minus 1/3. The first term is 1 over 4. So this is what happens. This is oscillating a little bit, but approach to 0. This value approach to 0. This is like idea. The another method is I want to use the theorem. What is the theorem? You think about limit and approach infinity, the absolute value of minus 1 to power n times 1 over n. You calculate. So what's that? This is like absolute value sign, always positive. You have to ignore minus 1 to power n. Same to limit n approaching infinity, 1 over n. The n is going to infinity. The what is like a 1 over infinity? The 1 over infinity is always 0. So absolute value is going to 0. Original one is going to 0. So we have two methods possible. That's right. This is going to 0. So the sequence minus 1 to power n, 1 over n. This is convergent. Convergent to 0. This is like idea by using this theorem. The next one. For what values of R is the sequence R to the power n convergent? So this is note. Limit of R to the x is infinity for R is greater than 1. The limit of R to the x as x approaches infinity is going to 0 for R is 0 and 1. I only give the one example. This is true or false. Here, the R equals 2. So what is the limit? X value approaching infinity, the 2 to the power x. So what is the answer? So answer is, what is the answer? Limit 2 to the x as x approaching infinity. Infinity? Infinity? Yep, you can sketch the graph. This is very clear. What's the graph of 2 to the x? Graph of 2 to the x is like this in chapter 6. This is 2 to the x. X value approaches infinity. The 2 to the x is approaches infinity. Yeah, this is true. This is true. So this one is, one example is limit. The x value approaches infinity. So 1 over 2 to the power x. The answer is like 0, because you can sketch the graph 1 over 2 to the x. What's the graph of 1 over 2 to the x? 1 over 2 to the x is decreasing graph. The next one, this is 1 over 2 to the power x form. X value approaches positive infinity. The 1 over 2 to the x approaches to x-axis like 0. The answer is 0. So we can replace the x by n. You can replace x by n, and the n, we have the same result here. And we have same result, so like this. As a minus 1 to 0, so what's that? The absolute value of R is between 0 and 1. The limit of R to the n is like 0. Does it make sense? So without absolute value sign 0, because we can use previous result. The previous result is here. Limit of absolute value of an is 0. Limit of an is also 0. We can use previous result here. So like this. So what does it mean? The R is between minus 1 and 0. So we think about limit of n approaching infinity, the absolute value of R to the n. You can calculate. This is same to limit. N is approaches positive infinity. So R is exactly change to the like this one. This absolute value of R is between 0 and 1. We have this result, 0 and 1. This is going to 0. So we have 0. We can use like a previous theorem, the limit of The without absolute value sign is also 0. This is one idea. But one more thing is you can use example. This is very helpful. The one example is limit the n approaching infinity minus 1 over 2 to the power n. What is the answer? So what is the answer? Limit of minus 1 over 2 to the power n as n approaching infinity. The answer is the 0. The 0. Yes. What is r? The r is minus 1 over 2. Here, minus 1 over 2 is between negative 1 and 0. The power is going to 0. We can use this result 0. Another way is you can use list of numbers. You can plug 1 into n minus 1 over 2. Plug 2, 1 over 4. Plug 3, minus 1 over 8. The plug 4, 1 over 16. So what happens? This value approaches like 0. So number is decreasing. This is very clear. The 이동 is fine. R equals to minus 1. So what's that? What is limit n approach infinity minus 1 to power n? The limit exists or does not exist? What is the answer? The limit exists or does not exist? Answer is does not exist. Is it right? Does not exist. What do you think? Does not exist. So same. You think about the list of numbers. You plug 1 into n. Answer is minus 1 is first term. Second term, you plug n equals to 2 into n. Minus 1 squared is 1. Plug 3, minus 1. Plug 4, 1. And keep going. So you can just sketch the graph. This is like n. This is 1, 2, 3, 4, 5, and so on. 1 has negative 1. 2 has 1. 3 has minus 1. 4 has 1. 5 has minus 1. So what happens? Just oscillating infinity many times. The gap is not decreasing. We have same gap too. We have same gap. This sequence is not going to only one finite number, oscillating between 1 and minus 1. Limit value does not exist. Like this. So we have it, the next one, diverges. So limit does not exist. We call sequence is divergent. So this is the whole idea. R is less than minus 1. What's that? Rn is divergent. We can use this diagram. I want to give some example. R is less than minus 1. One example is R equals negative 2. So we think about this sequence. Sequence is the negative 2 to the power n. You calculate limit. N approach infinity, negative 2 to the power n. So what happens? You can sketch the graph. This is very clear. So minus 2 to the n, you can use list of numbers. You plug 1, negative 2. Plug 2, negative 2 squared is 4. You plug 3, negative 2 cubed is minus 8. Plug 4, negative 2 to the power 4 is 16, and so on. You can sketch the graph. So what happens? Graph is like this. So 1 has negative 2. 2 has 4. 3 has negative 8. 4 has 16. What happens? Like oscillating. So the other part approaches negative infinity. The negative 2, negative 8, negative 32 going to minus infinity. The even thing is 4, 16, 64 is going to positive infinity, oscillating infinity many times. So going to the infinity and the minus infinity, limit value does not exist. Limit value does not exist. So what happens? Sequence diverges. This is like idea. So we have this conclusion. The R is between -1 and 1. The sequence R to the N converge to the zero. R equals 1, very clear. 1 to power N is just 1, converge to 1. R to the N is diverges for R is less than or equal to -1, the greater than 1. Here is right. The greater than 1 here. R is greater than 1, diverges. R is greater than, less than -1, diverges. R equals -1, yes, diverges. We can combine three cases. This is like the idea. So the one example problem is given is like this. Sequence -5 to the power n. This is converges or diverges. So what is the answer? -5 to the n is converges or diverges. What is the answer? Could you decide the which one? The converges or diverges? Answer is, so what do you think, other guys? Converges or diverges? Is it like diverges? Is it right? So same. What's it like R? The R equals -5. This R is like the -5. This -5 is here. The R is -5. -5 is less than or equal to -1. Exactly. Last case. Sequence diverges. Answer is diverges by using this table. So very useful. The next one. Determine whether n plus sine of n over 5n plus 1 converges or diverges. So how can solve? Take limit. This is like idea. You can use take limit. Limit n plus sine of n over 5n plus 1. This is converges or diverges. What do you think? Converges or diverges? What do you think? How can you solve? The limit of n plus sine of n over 5n plus 1. How can you solve this problem? So n is going to infinity. So this is exactly infinity plus sine function is oscillating between -1 and 1. So infinity -1 or infinity plus 1. This is infinity. The bottom one, 5 times infinity plus 1 is infinity. Infinity plus infinity. Don't use L'Hopital's rule. We have the sum of trig functions is given. Usually doesn't work. So like L'Hopital's rule, don't use L'Hopital's rule. In this case, you can multiply top one and bottom by the next one, the 1 over n. You can distribute 1 over n. So here, what's that? This is limit. So like this, distribute 1 over n. N times 1 over n is 1. N times the sine of 1 over n times the sine of n is sine of n over n, the same. Distribute 1 over n. So 5n times 1 over n is 5. 1 times 1 over n is 1 over n. The next thing, n is approaching infinity. Was it like this one? The n is approaching infinity. Was 1 over n? Yes, 1 over infinity is going to 0. What's the sine of n over n? In this case, we can use squeeze theorem. The sine of n is between -1 and 1. is right, like this. You can divide each side by n. So next, take limit, infinity, take limit, and approach infinity, so take limit, and approach infinity. What's it like left-hand side? The limit of minus 1 over n as n approach infinity is, what's that? What's the left-hand side? Yep, this is 0. What's the right-hand side? What's the limit of 1 over n as n approach infinity? This is also the 0. What's it like? Yeah, thank you. What's the middle one? Middle one is going to 0. So we can use squeeze theorem. This is called squeeze theorem. Squeeze theorem. So this is going to 0. So what's it like remaining things? Remaining thing is 1 over 5. Answer is 1 over 5 by using squeeze theorem. This is the idea. Like this. So sequence converge to 1 over 5. This is answer. This is answer. The next one is indeterminate forms and L'Hopital's rule. So limit of a n over bn is n approach infinity, the infinity over infinity or 0 over 0 form. So limit of a n over bn equals, you can use L'Hopital's rule. Limit of a n prime over b to the n prime. The limit of a n times bn is 0 times infinity. Limit of a n minus bn is infinity minus infinity. Limit of a n to the power bn is 1 to infinity, 0 to 0, infinity to the 0. Convert them to the quotient forms and use L'Hopital's rule. This is like a whole idea for solving this kind of problems, right? The L'Hopital's rule, section 6.8 is very useful for checking the sequence is convergent or divergent. Example, the limit of n squared times sine of 1 over n squared. So what happens here? This n squared approach to the infinity. You plug infinity into here, the 1 over n squared approach to the 0. What is sine of 0? What is sine of 0? Sine of 0 is 0. Yes, 0. Exactly 0 times infinity. How can you solve? Convert this one to the quotient form. What's the quotient form? Quotient form is like a fraction. And change it to the fraction. How can you change it? This is the idea. Limit and approach infinity. You can keep trig function at the top. Trig function is sine of 1 over n squared. Trig function at the top over. The n squared is going to denominator by using reciprocal. Like this. So what's that? N is going to infinity, exactly plug infinity into n. Sine of 1 over infinity is 0. The bottom one, 1 over infinity is 0. Exactly 0 over 0 form. So 0 over 0 form, you can use L'Hopital's rule. So you can use L'Hopital's rule. Like this. So this is same to limit. And approach infinity, you can use chain rule. What's the sine prime? Outer function is sine. What's the sine prime? The derivative of sine is, remember, what's the sine prime? Do you know chain rule? Yeah, cosine. Cosine of inner function 1 over n squared times inner function prime. Inner function prime is 1 over n squared prime over 1 over n squared prime. The bottom one is same. So what happens? 1 over n squared prime crossed out. Answer is limit and approaches infinity. cosine of 1 over n squared. The n is approach infinity, the 1 over n squared approach to the 0. What is cosine of 0? What is cosine of 0? Cosine of 0 is, yep, this is 1. So what is your final answer? Sequence n squared times sine of 1 over n squared. The sequence converges. Sequence converges to, to 1. This is the answer, right? This is the whole idea for solving this kind of problems. Like this. So this is very useful. So next one. So do you know relative rate of growth for limit f of n over g of n is infinity over infinity form? So this is like, you can go check my lecture note, section 6.8. So very similar one. So only replace x by n. You can check my lecture note in section 6.8, very similar. Only difference is I replace it x by n. This is the only difference here. So one more, we can add one more term. N factorial is growing faster than any exponential function, the slower than n to the power n. This is only one difference. The other part is same. We have 2 ln function is very slow. Only 1 ln function is growing faster than 2 ln function, right? So what does it mean? The one example is here. What is limit? N approaches infinity. The ln of ln n to the power 100 over only 1 ln to the power 1/2. What is the answer? So what is the answer? So 0 is right? 0? Yes, 0. Because beta is 1/2. Alpha is 100. So ln to the 1/2 is growing faster than ln of n to the 100. So bottom one is growing faster than top one. Answer is 0. So that's it. This is the idea. So one more limit. N approach infinity, the n factorial over 100 to the power n. What is the answer? So what is the answer? Limit of n factorial over 100 to the power n. So what is the answer? You can use relative rate of growth. Like answer is the infinity. So what do you think? What do you think, other guys? Yes, here, this is n factorial here, 100 to the power n. N factorial is growing faster than, yeah, thank you, all of guys. This is 100n. Top one is growing faster than bottom one. Answer is infinity. So that's it. This is the idea by using relative rate of growth. So I want to give one more example. So this problem. You can take limit. Only think about first one. N is approach infinity. Top one is infinity. Bottom one is infinity. Infinity over infinity form. N is going to infinity. Infinity over infinity form. Yes, we can use relative rate of growth. You have to ignore constant. You can compare. ln of n to the 200 is here. So ln of n 20 is here. So ln of n 20 is growing faster than ln of n to the 200. Ignore slow one. You can compare only two things. This one and this one. We have only one thing here. Next, compare. N of n to the 20 over, you can change it. The fifth root of n is nth root, the n to the power 105. So we have ln of 20 is here. N to the 105. The n to the 105 is growing faster than ln of n to the 20. So bottom one is growing faster than top one. Answer is 0. So what's the answer? The sequence converges to 0. Converges to 0. This is like a whole idea for solving this kind of problem by using relative rate of growth. This is the idea. The next is, so we think about this one. Sequence AN is increasing. So what's that? The AN is less than AN plus 1 for all n is greater than or equal to 1. The exact meaning is here. A1, A2, A3, next one, increasing. Does it make sense? One example is A1 is 1, 2, 3, 4, like this. This is, yes, greater, 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 increasing. You can draw graph. This is like n. 1 has 1, 2 has 2, 3 has 3, like, yes, increasing. This is like a definition. Decreasing, opposite direction. So AN is greater than or equal to AN plus 1 for all n. We have the like this, is right? A1 is greater than A2, the greater than A3, or something like that. Here, 1, 1 over 2, 1/3, the 1 over 4. This is like decreasing, is right? This is unequal to like this. You can draw graph. 1 has 1, 2 has 1 over 2, 3 has 1/3, like is decreasing. The sequence is decreasing. Other like a monotonic, the either increasing or decreasing. Either increasing or decreasing, we have monotonic. This monotonic. Definition. Another definition, the AN is bounded above. So there is a number m such that AN is less than or equal to m for all n greater than or equal to 1. So what's like AN is bounded below. So if there is a number, the little m, such that the AN is greater than or equal to little m. For all n is greater than or equal to 1. So AN is bounded. So this is bounded above and below. So I want to give the one example here. Sequence here. We think about simple one. Sequence and square. The first one, you can check. This is monotonic or not. It's monotonic. What is like definition of monotonic? Increasing, either increasing or decreasing. So my question is, the sequence and square is monotonic. So what do you think? The monotonic? Yes. You can plug a number here. You can plug 1 square, 2 square, 3 square. What happens? Number is greater, 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 exactly increasing. So monotonic. Yeah, this is increasing, the monotonic. So bounded above or not? Do you have this kind of number? M is like AN is less than or equal to M. Is it possible? No, we don't have it. This sequence is increasing till going to what? Infinity. We don't have this kind of number. Is it like AN is less than or equal to M, not bounded above? No. The bounded below? Bounded below? We have like a small number M. The sequence AN is the greater than or equal to small number M. Do we have a small number like this? So bounded below or not? Yes, yeah, here. All sequences like 1 square, like 2 square, and 3 square. Yes, this is always greater than equal to 0. Or 1, it doesn't matter. We have something infinitely many possible numbers, small m. Yes, bounded below. Bounded below. So one more, we think about monotonic sequence theorem. What's like a monotonic sequence theorem? Every bounded monotonic sequence is convergent. So this is one more important theorem. Every bounded monotonic sequence is convergent. This is the idea. Here, this sequence is, in this case, is monotonic, just increasing, bounded below and above. Bounded below and above, exactly bounded. What's it like definition of bounded? Bounded below and above. We have bounded below and above. We have two numbers. What happens? Just increasing and bounded above. So what happens? Approaches some number. Approach some number. This is always convergent. Always convergent. Here, prove that n over n plus 1 converges by using monotonic sequence theorem. So first one, n over n plus 1 is, you can plug 1, 2, 3, and so on. What happens? 1 over 2 is your first term, plug 2, 2/3. 3 over 4, 4 over 5, 5 over 6, 6 over 7, 7 over 8, so like this. So first one, this sequence is monotonic. Was it like a monotonic? The either increasing or decreasing is right. This is exactly monotonic. Increasing or decreasing. So what do you think? This sequence is monotonic. Yes. Yep. The monotonic. You can draw the graph here. This is 1 over 2, 2/3, 3 over 4, something like that. Yes, just increasing. Another one, greater, 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 greater. Yes, just increasing monotonic. This increasing the monotonic. So one more. So how can you check this is like a convergent or divergent? We are going back to here. So this theorem, we can check monotonic. You check bounded. This is bounded. This is bounded. Was it like this is bounded or not? So sequence n over m plus 1 is between small number m, bigger number m. So this is like a definition of bounded. Do you have little m and capital M? Do we have this kind of numbers? Do we have these numbers? The little m and the capital M? Do we have this one? Yes. Here, 1 is like maximum. This value is always less than or equal to 1. So another one, this is always positive. Yes, greater than 0. The between the 0 and 1. So this is exactly bounded. The bounded. So n of n plus 1 is bounded. We can use monotonic sequence theorem. What's that? Increasing is exactly monotonic. The sequence is monotonic and bounded. Answer is converges by using monotonic sequence theorem. This is like a whole idea for solving this kind of problem. Okay, so this is all for today's lecture. So if you have any question, please write your question on the chatting board. I answer your question. If you don't have any question, you can only like leave this live session. The one more, if you have any question in your homework, everything, you can only write your question on the like discussion board or send email, some the I and Kasha help you. All of things. Okay. You're welcome.